In the unforgiving laboratory of modern warfare, Ukraine has engineered a profound transformation. Captured Russian military hardware, recovered from the battlefield at immense human cost, is no longer mere scrap or symbolic victory. It has become raw material for deep scientific exploitation through TrophyLab, the secure platform launched by Ukraine's Ministry of Defense in mid-June 2026. This vetted access system centralizes reverse engineering, materials analysis, electronic dissection, and performance evaluation of over 115 distinct samples spanning 79 categories, supported by more than 225 technical studies from Ukrainian laboratories. TrophyLab formalizes years of ad hoc battlefield recovery and analysis. Ukrainian combat engineers and special recovery teams risk their lives to secure intact or partially damaged systems before they can be destroyed or sabotaged. These items are transported to secure facilities where multidisciplinary teams, mechanical engineers, material scientists, electronic specialists, propulsion experts, and software reverse engineers conduct exhaustive examinations. The resulting data, including high-resolution scans, chemical compositions, circuit schematics, firmware extractions, radar cross-section measurements, and failure mode analyses, are uploaded under strict security protocols for sharing with approved allies. Let us examine some of the most significant captured systems and the transferable scientific and technological insights they provide. The T-90M main battle tank. This represents Russia's premier operational armored platform, featuring the Kalina fire control system, Sosnet-U thermal imaging, relict explosive reactive armor, and an advanced active protection precursor. Ukrainian analysis reveals detailed metallurgical profiles of its composite armor arrays, including layered ceramics, rolled homogeneous armor, and reactive elements. Engineers can measure exact thicknesses, bonding techniques, and defeat mechanisms against kinetic energy penetrators and shaped charges. Insights into the tank's autoloader mechanics, 2A46M-5 smoothbore gun dynamics, and thermal sleeve performance under sustained fire expose limitations in crew ergonomics and ammunition handling under combat stress. Electronic vulnerabilities in its sensor fusion suite and command and control links allow development of more effective electronic warfare spoofing techniques. Partners can replicate and improve upon these armor packages, design superior anti-tank munitions tuned to specific weak points like turret ring junctions or engine compartment cooling vents, and enhance their own vehicle survivability through data-driven modeling of real-world ballistic impacts. The Kork 47M2 Kinzhal air-launched ballistic missile, marketed as a hypersonic breakthrough, recovered specimens and fragments provide unprecedented access to its Iskander-derived design. Analysts study the solid propellant rocket motor grain structure, burn rate profiles, and high-temperature resistant composite casings engineered to withstand Mach 10 aerodynamic heating. The guidance package, combining inertial navigation, GLONASS satellite updates, and terminal seeker, yields critical telemetry on maneuverability envelopes, plasma sheath effects on radio frequency propagation, and actual circular error probable in contested environments. Material scientists examine ablative coatings and refractory alloys that manage extreme thermal loads. These insights accelerate development of advanced hypersonic interceptors, improved early warming sensor fusion to detect and track quasi-ballistic trajectories, and hardened materials for defensive infrastructure. Countermeasure designers gain data to refine directed energy weapons or electronic disruption techniques targeting the missile's guidance vulnerabilities during its terminal dive phase. Loitering munitions and strike drones, particularly the Zala Lancet series. Captured Lancet 3 variants offer deep insights into composite airframe construction using carbon fiber and polymer matrices optimized for low radar cross-section and structural efficiency. Propulsion analysis covers electric ducted fans and internal combustion variants, including power-to-weight ratios, endurance profiles exceeding 30 to 40 minutes, and fuel or battery chemistries. The electro-optical infrared seeker heads reveal imaging algorithms, stabilization systems, and target recognition software trained on military hardware. Communication links, often using frequency-hopping spread spectrum or encrypted channels, expose vulnerabilities to jamming and spoofing. By dissecting these, engineers can develop superior counter-drone systems, including AI-driven spectrum analyzers, high-power microwave-directed energy weapons, and next-generation GPS-denied navigation that outperforms Russian implementations. The warhead configurations, shaped charges, or fragmentation patterns inform both defensive armor layering and offensive munition optimization, partners can copy refined aerodynamic profiles, autonomous terminal guidance routines, and cost-effective manufacturing techniques for scalable drone production. Reconnaissance and strike UAVs such as Orlan 10 and Zala Aero platforms. These provide extensive data on resilient navigation in jammed environments, using inertial measurement units combined with terrain contour matching and visual odometry. Captured examples allow extraction of flight control firmware, revealing Russian approaches to redundancy and fail-safes. Antenna designs and date-length frequencies inform electronic warfare libraries for rapid jamming waveform generation. Materials analysis of lightweight composites and modular payload bays accelerates development of longer endurance, more survivable reconnaissance drones with improved sensor suites. Electronic warfare and radar systems. Captured Krasuka or Boris Oglep's 2 complexes yield detailed emitter characteristics, including power output levels, modulation schemes, and phased array antenna beamforming algorithms. Spectrum analysis identifies exact operating bands for radar-guided munitions and communications jammers. This data enables creation of more sophisticated cognitive electronic warfare systems capable of real-time threat emitter classification, adaptive countermeasures, and even offensive cyber-electronic attacks on Russian command networks. Precision-guided munitions and unexploded ordnance. Recovered Iskander-M missiles, FAB glide bombs with UMPC kits, and various rocket artillery systems allow examination of inertial guidance packages, satellite-augmented navigation modules, and fuse arming sequences. Propellant chemistry in solid rocket motors reveals burn rate modifiers and stability under thermal cycling. Explosive fills and shaped charge liners provide insights into detonation velocities, bracings, and metal jet formation for improved counter-battery and intercept technologies. Unexploded ordnance offers rare opportunities for safe disassembly, mapping of safety mechanisms, and identification of manufacturing defects that can be exploited in electronic attack scenarios. Smaller but critical components. Night vision and thermal optics from captured vehicles and infantry kits expose Russian image intensifier tube generations, microbolometer arrays, and cooling technologies. Radio equipment reveals software-defined radio architectures, encryption standards, and frequency agility patterns. Knowledge essential for developing interoperable, jam-resistant, NATO-compatible systems or superior alternatives. From these captured systems, transferable technologies are extensive and scientifically rich. Material scientists gain real-world data on Russian titanium alloys, carbon-carbon composites, and energetic materials under operational stress, accelerating development of lighter, stronger armor and airframes. Electronics engineers extract and analyze Russian microprocessors, field programmable gate arrays, and power electronics, identifying supply chain dependencies on foreign components despite sanctions. Software teams reverse engineer embedded algorithms for target tracking, autonomous navigation, and sensor fusion, informing defensive AI systems that can predict and preempt Russian drone swarms or missile salvos. Propulsion experts study ramjet and solid rocket efficiencies, while aerodynamicists map control surface effectiveness at transonic and hypersonic regimes. The cumulative effect shortens the observe-orient-decide-act loop dramatically. Instead of speculative modeling, engineers work with empirical data from systems tested in the harshest conditions, actual combat. TrophyLab's physical sample request system elevates this further. Approved partners can conduct non-destructive testing via computed tomography, spectroscopy, and acoustic emission analysis, or proceed to sectioning, finite element validation of stress distributions, and live environmental testing. This bridges the gap between intelligence and applied engineering, enabling rapid prototyping of countermeasures that have already proven effective against Russian tactics. Strategically, TrophyLab creates a virtuous cycle of attrition and innovation. Every Russian system destroyed or abandoned feeds the knowledge base, strengthening Ukrainian defenses and those of global partners. It democratizes high-fidelity threat intelligence, particularly valuable for nations operating legacy Soviet equipment who can now accurately assess vulnerabilities and upgrade priorities. Security protocols remain stringent. The closed platform, encrypted access, and monitored usage protect sensitive Ukrainian methods while preventing technology leakage. This ensures that analytical advantages remain one step ahead of Russian adaptations. In essence, TrophyLab represents asymmetric warfare at its most intellectually sophisticated, through meticulous scientific exploitation of captured hardware, from the molecular composition of armor ceramics to the algorithmic heartbeat of drone autopilots. Ukraine converts enemy mass into collective knowledge. The platform does not merely catalog weapons, it dissects their DNA, maps their weaknesses, and broadcasts blueprints for superiority. As more samples flow in and international collaboration deepens, TrophyLab will drive breakthroughs in hypersonic defense. What Russian engineers designed in secrecy, Ukrainian scientists and their partners now expose under laboratory lights, turning the tide not just through firepower, but through superior understanding of the physical and digital realities of the battlefield. This is innovation forged in fire. Every circuit board analyzed, every warhead fragment measured, and every line of code decompiled becomes another layer in the shield protecting democratic nations. TrophyLab stands as a powerful declaration. In the 21st century, knowledge harvested from the front lines is the ultimate strategic resource, and Ukraine has ensured that this resource serves the cause of freedom and technological progress for the world.